On Friday, we talked about the different types of, we talked about the fact that when you take an acid and you mix it with a base, in the correct and proper amounts, you get a neutralization reaction. And the neutralization that you almost always get is water and some type of ionic salt, which is why the homework assignment that included the naming, I had you write those double replacement reactions. And in those double replacement reactions, we had something like an acid reacting with a base to produce water and some type of salt. Okay? So in this case here, that's what happens with a neutralization reaction. Now, the other thing that's important to understand is that there are definitely types of calculations that we can do with neutralization reactants. One of the things is that if we can determine the moles of one reactant, we can figure out the moles of another reactant using stoichiometry. We can also use the molarity formula in order to figure out moles of something, or molarity of something, or volume of something in the reaction. So we'll get to those types of calculations in a second, but you should be aware of the three common reactions that involve strong acids and or strong bases. The scope of this class will not spend a lot of time talking about the neutralization reactions of weak acids and strong bases, or weak bases and strong acids, but you should be aware that they exist. Now, strong acids and strong bases undergo a double replacement reaction to make water and an ionic salt. So remember, the basic definition of ionic salt is basically any metal paired up with a nonmetal or a polyatomic ion will make some type of ionic salt that's usually soluble in water. So in this case, we have an acid, H2SO4, reacting with a base, LiOH, to make, so we have an acid reacting with a base to clearly make water, and again, a salt. Okay? Now, another type of reaction is that strong acids can react with active metals in a single replacement reaction to make hydrogen gas and an ionic salt. So in this case, we have strong acid hydrochloric acid reacting with the metal iron to make the ionic salt iron 3 chloride and hydrogen gas in this case. And then the last type of reaction that you should be aware of is the double replacement reaction between Na2CO3. So in this case, we call it an ionic carbonate. So I have something like Na2CO3 plus HBr. According to the double replacement reaction rules, you would see something that looks like this. The issue is that the H2CO3 doesn't actually form. That is the appropriate double replacement reaction for a strong acid and an ionic carbonate, but when the H2CO3, which is known as carbonic acid, forms, it doesn't stay as carbonic acid. It actually further decomposes into water and carbon dioxide. So if I give you a reaction like this on the test, you have to know that the H2CO3 will not stay around and it has to break apart into water and carbon dioxide. If you don't write that, you will get points taken off. So you have to know that if you see a product in a double replacement reaction that is H2CO3, that is carbonic acid, you have to know that it breaks apart into water and carbon dioxide. Any questions? It's more stable form because in AP chemistry we would say that the H2CO3 would further decompose into water and carbon dioxide because water and carbon dioxide are significantly more stable than the H2CO3, and that's the short story. The long story is a little more complicated, but that's basically it. Now, some example problems that we should probably try to work through here. So in this case, we're asked to calculate the volume of 2 molar or 0.2 molar potassium hydroxide needed to completely neutralize 75 mils of 0.125 molar H2SO4. So in this problem here, I'm going to write the reaction first. So I'm going to take the KOH plus the H2SO4 will react to form. One of those things is going to be water, so I'm going to have HOH, and the other thing that's going to form is my ionic salt, which in this case is going to be K2SO4. So because I'm telling you that the KOH is a solution, I know that it is aqueous. And one thing that you might want to start making sure that you understand or always thinking about is that any time that you see an acid, unless it's otherwise stated, it will also be aqueous. Now, when we say that water is formed, one of the things that we talked about when we talked about things that drive a double replacement reaction, one of them was a precipitate formed, one of them was a gas formed, and one of them was pure liquid water. So when water is a product, it's always going to be pure. And then because it's an ionic salt, that's going to be a solution, so this is going to be aqueous. The next thing we need to do is we need to balance this, and I don't think it's balanced as it's written, so I'm going to want to put a coefficient of 2 here and a coefficient of 2 here, and everybody is happy. Now, I need to go through and take the information that I have and figure out what to do with it. So in my potassium hydroxide, I have the molarity, which is 0.200 molar, and I need to find the volume, which is liters usually, and I don't know moles yet, but we're going to get there. For my acid, I know that the molarity is 0.125 molar. I don't know the moles, but I think I can calculate it when I know that the volume, in this case liters, is 75 milliliters, which I'm going to convert right away to liters. Liters. So what I'm going to do is the first thing I'm going to do is I'm going to go ahead and calculate moles of H2SO4, because in any chemical reaction, if I know moles of one thing, I can calculate a whole lot of things using stoichiometry. So first thing I'm going to do is say that molarity is equal to moles over liters. I know that the molarity in this case is 0.125 molar H2SO4. So that's going to be equal to moles of H2SO4 over 0.0750 liters. So 0.125 times 0.075 gives me 0.009, let's see, 1, 2, 3 sig figs, 3.8 moles of H2SO4. Okay, so I now know moles of H2SO4, and because I know moles of H2SO4, I can calculate moles of KOH. But when I go moles of something to moles of something, what do I need to know, find, or calculate? The mole ratio, right? So in this case, the ratio is 1 mole of H2SO4 to 2 moles KOH. So I'm going to take the 0.00938 moles of H2SO4, and I'm going to convert that to moles of KOH. So 1 mole of H2SO4 is equal to 2 moles KOH. So when I plug that in the calculator, I take the 0.00938 times 2, I get 88, because 3 sig figs, moles of KOH. So now that I know my moles of KOH, I'm going to put that here. Well, I'm going to just draw an arrow. So I'm going to do this. Okay. So now I can go ahead and use that information to help me to find out volume of KOH. So molarity is equal to moles over liters. 0.200 molar KOH is equal to moles KOH over, oops, not moles. Let me, hold on. Let me back this up a second. Just got a little carried away here. All right. We know that this is, 0.0188 moles of KOH. Oh, man. I didn't write this right. My bad. Why can't I? Oh, there. Why? This should be 0.0188. Sorry. Okay, anyway, it's over liters though. And through the magic of some math, right, I can figure out the volume. So I'm going to take liters to the other side and divide by molarity. So liters is going to be equal to 0.0188 moles of KOH over 0.200 molar KOH. So 0.0188 divided by 0.2 gives me a volume in this case of 0.0940 liters or 94.0 milliliters. Now, I must caution you in this unit, and the reason why I have to throw this caution out there is that sig figs are going to become a problem for some of you. Because more often than not, when we're doing these types of calculations, the calculator is not going to add that 0.0940, that last zero. It's going to go to 0.094. And in this particular problem, all of the sig figs were 3 sig figs. And if you don't report that last zero, you are going to get points taken off. So be aware of that. Now, another problem. In the next problem, you have 65 milliliters of 0.1 molar hydrochloric acid solution, and it's needed to neutralize 25 milliliters of calcium hydroxide solution with an unknown molarity. Determine the molarity of the calcium hydroxide. So, in this case, I know my hydrochloric acid, and I'm going to write that formula. Let's see. Hydro tells me it's a binary acid, so that's hydrogen and one other nonmetal, which in this case is chloride, so it's going to be HCl, and it's a solution, so that's going to be aqueous. Is going to react with the calcium hydroxide, also a solution, so that's aqueous. And it's going to be neutralized, so that tells me that I'm going to make water, which will be a pure liquid. And then we're going to have, let's see, we're going to have our salt, which is Ca and Cl2. Okay, so in this case, I know that the ionic salt is going to end up being aqueous because it'll end up dissolving in the water. So now we need to go ahead and balance this equation. My hydrogens appear to be balanced. My hydroxides are not, so I'm going to put a coefficient of 2 there. I'm going to put a coefficient of 2 here, and now everybody's balanced. So now I'm going to go ahead and look at what I know. So in this case, I know the molarity of my hydrochloric acid is 0.100 molar. I don't know moles, but I do know the volume, in this case, is 65.0 milliliters times 1 liter over 1,000 milliliters will give me 0.0650 liters. So what do I know about my base? I don't know the molarity, but that is what I'm being asked to determine. I also don't know my moles, but I think I'm going to have to calculate that. But I do know my volume, which is 25.0 milliliters, or 1 liter over 1,000 milliliters is 0.0250 liters. Okay, so what I'm going to do here is, in this case, one of my reactants I know 2 things for, so that's the one I'm going to work off of. I'm going to determine moles. So I'm going to take molarity is equal to moles over liters. So in this case, it's 0.100 molar HCl is equal to moles of HCl over the 0.0650 liters of HCl. So 0.1 times 0.065 gives me 0.0065 moles of HCl. So that tells me moles of HCl. And what moles of HCl allows me to do is figure out moles of calcium hydroxide. So I'm going to take the 0.0065, should be a 0 here, moles of HCl, and I'm going to convert it to moles of calcium hydroxide. And when I do that, I need the mole ratio. So I know that the ratio is 2 moles of HCl for every 1 mole of calcium hydroxide. So I'm going to put my 1 mole calcium hydroxide on top and my 2 moles of HCl on the bottom. So 0.00650 divided by 2 gives me 0.00325 moles of CaOH2. So I'm going to take this guy and go right there. So now I can now determine the molarity because that's what the problem is asking me to do. So molarity is equal to moles over liters. Molarity is equal to 0.00325 moles of CaOH2 over the volume, which we just decided above was 0.0250 liters. So 0.00325 divided by 0.0250, oops, 0.00325 divided by 0.0250, I get something like this. Molarity is equal to 0.130 molar CaOH2. So there's that. So we had to calculate molarity, we had to calculate volume, and we're going to do one more example. It's a little bit different. And then you're going to have some time to work, maybe. All right, so in this case here, it says magnesium metal can be replaced with nitric acid in a single replacement reaction. So what I'm going to do is I'm going to write this reaction first of all. So I'm going to take my magnesium metal, which is a solid, can be reacted with nitric acid. Let's see. IC tells me it's the 8 ion, and that tells me that it's nitrate, which is NO3 minus 1. And because it's an acid, we have to put a hydrogen there. So it's going to be NO3, which will be aqueous. And when this reacts, I'm going to make magnesium, some type of an ionic salt, and I'm going to make hydrogen gas. So in this case, I'm going to get Mg, oops. Yeah. No. Undo. No. Okay, all right, sorry. I'm going to get Mg NO3 2, and I'm going to get hydrogen gas. Well, if hydrogen is a gas, I have to take that and put that there, and then this is going to most likely be aqueous because that's how these work. So now I need to go ahead and balance this reaction. My magnesiums are balanced. I need to put a coefficient of 2 here. That gives me 2 nitrates and 2 hydrogens, and it looks like everybody's balanced after that. So the first question says, what is the mass of magnesium to completely react with 55 milliliters of 0.75 molar nitric acid? Well, what I'm going to do is I'm going to go ahead and first of all figure out what I have and figure out what I can solve for. So molarity, molarity is equal to, in this case, 0.750 molar HNO3. I don't know moles, but I do know volume. In this case is 55.0 milliliters, which 1 liter over 1,000 milliliters will give me 0.0550 liters. So that tells me that I can probably solve for moles. So what I'm going to do is I'm going to take molarity is equal to moles over liters, which is 0.750 molar HNO3 will equal moles of HNO3 over these 0.0550 liters. So 0.750 times 0.0550 will give me 0.0413 moles of HNO3. So now if I know moles of HNO3, I can convert it to moles of magnesium and eventually to mass of magnesium using stoichiometry. So I'm going to take 0.0413 moles of nitric acid, and I'm going to convert it to moles of magnesium. Well, the ratio that I need for that is 2 moles of HNO3 for every 1 mole of magnesium. So my 1 mole of magnesium is going on the top, and on the bottom I'm going to have my 2 moles of HNO3. And to get to grams, which is what I'm trying to do, I need to remember that in 1 mole of magnesium, the molar mass of magnesium is 24.30 grams of magnesium. So when I plug this in the calculator, 0.0413 divided by 2 times 24.30, I get something like 0.502 grams magnesium. So that tells me that I need 0.502 grams of magnesium, roughly half a gram of magnesium, to react with all of the nitric acid. Okay? Now, what I'm going to do is go to the next page here, but in order to do that, I'm going to take this guy with me. Nope, that's not what I wanted. All right, so to the original problem from above, we can either grab moles from here. That's one way to do it. Or we can get moles from grams, so I'm going to do that. I'm going to say that if we determined the number of moles of nitric acid, we can just do a stoichiometry problem to get moles of magnesium. So this page says, so if I have the magnesium, which is a solid, plus the HNO3, which was aqueous, reacts to form the magnesium nitrate plus the H2, which was gas, like that, okay? Now, we also balanced that before by saying it was 1, 2, 1, 1. And then this one says if all of the magnesium reacts completely, what volume of hydrogen measured at 22.5 and 1.15 ATM will be collected? So what type of a formula do you think you're going to probably end up using here? It's not a stupid one. It's a pretty common one. What's the formula?
I don't know. It's not one formula.
It is that one.
That has like a temperature in it.
Ooh. There's a temperature in it.
D.
It's not a D though. R, there's an R in it. Oh, yeah. It's PV equals nRT. So we had PV equals nRT. Now, there's a couple of things that we know for sure here. We know that R is always 0.0821 liters ATM moles Kelvin. We're given our pressure here, which is 1.15 ATM. We're given a temperature here, which is 22.5 degrees Celsius plus 273 will be 22.5 plus 273 is, let's see, 295.5 Kelvin. And we're asked to find volume here, but we don't have moles, or do we? I don't know. So here's the thing. There's 2 ways we can get moles. If we go back, so I'm going to take the 0.502 grams of magnesium, and I'm going to convert that to moles. So in 1 mole of magnesium, I have 24.305 grams of magnesium, which 0.502 times 24.305 not 5, just 30. Okay, I get something like, whoa, what happened here? Oh, I did the wrong math. 0.502, that'd be divided by 24.30, would be 0.0207 moles of magnesium. Well, there's another way too, right? So I'm gonna go back. If we had 0.0413 moles of HNO3, and I wanted to figure out moles of nitric acid, I could take my 2 moles of HNO3 and my 1 mole of magnesium and get, let's see, 0.0413 divided by 2 gives me still 0.0267, nope, I should write it right, 0.0207 moles of, wait a minute, that's literally the same answer. Weird how that worked out. So what I'm going to do is I'm going to take that and plug it up here, 0.0207 moles of, that's my moles of magnesium, right? But the issue is that we're trying to get hydrogen gas, so I have to go one step further. 1 mole of hydrogen gas for every 1 mole of magnesium, and that gets me 0.0207 moles of hydrogen gas. Huh. Cool. So now, PV equals nRT if P is 1.15 ATM, and we're looking for volume, and we know that moles is 0.0207 moles of hydrogen times R, which is 0.0821 liters ATM moles Kelvin. I got to move all this business over here. Times temperature, which we said was 295.5 K. The magic of math says that if I take the 0.0207 times 0.0821 times 295.5 divided by 1.15, I get something like 0.0437 liters of hydrogen gas, or 437 milliliters, whichever is fine. But that's basically what we're doing here for the homework for today. So your homework